Sometimes there's a set of vectors in a vector space that all by itself forms a smaller vector space inside of the big vector space. And when that happens, it's called a subspace. Let's look at some of the vector spaces we know and then think about some subspaces of them. So there's functions of x, polynomials in x, real sequences, which we could write as row vectors or column vectors, and then m by n matrices with real entries. So we showed that all of these form vector spaces. And let's think about a subset of a vector space here and check and see if that forms a vector space. Now all of these are defined so intrinsically on the real numbers that all those properties of addition and multiplication of the real numbers are definitely going to hold. So we have 4 properties to think about. And actually, if we're working inside of a big space that we already know is a vector space, we can eliminate 2 more of these properties. So first of all, if the big space has a 0 and the space inside is closed under scalar multiplication, then let's note, so let's let U be inside of V a vector space. So since V has a 0 vector, if U is closed under scalar multiplication, then that means that 0 times V, now this is the scalar 0, I put a bar on that 0 to mean the 0 vector. The scalar 0 times some element is going to be the 0 vector of the space. So if we know that U is closed under scalar multiplication and it's inside of V that has a 0 vector, then scalar multiplication is going to take care of having the 0 vector be in U also. So we can really erase number 3 here. And then for almost the same reason, since V has additive inverses, so that is negative V, negative little v for every little v that's in big V. If U is closed under scalar multiplication, then we could multiply by the scalar minus 1 times V, and then we're going to get a negative V. And since we're closed under scalar multiplication, that negative V, which is the inverse of little v in the vector space big V, is going to be in the space U. So we actually don't even need to check for additive inverses anymore if we're a subspace of a bigger space. So to see that a subset of a vector space is a subspace, we really need to check only 2 things. And these things are not easy to see just from the bigger space. It's easy to find examples where we're not going to have closure under addition, or we're not going to have closure under scalar multiplication. But let's look at some examples of potential subspaces. So for example, let's look at all the points A1, A2, A3 in R3, so real triples, with Actually, with A2 equals 0. So maybe I could have written the set of all vectors A1, 0, A3 in R3. So let's check closure under addition. If we add two vectors that look like that together, are we going to get a 0 in the second component? Well, of course, we'll have 0 plus 0 in the second component, which is 0. Something in the first component may or may not be 0. Something in the third component may or may not be 0, but we'll definitely get a 0 in the second component. And scalar multiplication. If we take a vector like that, we multiply it by some scalar k, we'll get ka1 here, ka3 there, and 0 in the second component. So that is closed under scalar multiplication also. Since it's closed under addition and scalar multiplication, and is part of something else that we already know is a vector space, then it's a vector space also. So this is a subspace of R3. Let me write down those two conditions here. So we had to check that A10, A3, and B10, B3 being in the space. Let's call this space V. Imply that the sum is also in V. And the sum, of course, is A1 plus B1 up here, 0, A3 plus B3 down there. That's definitely in B. Also, if we have one of these in V, that means that K times one of these which is Ka1, 0, Ka3 has got to be in V. So therefore, it's a subspace of the vector space R3. And it looks just like R2 in some sense, because all the mathematics that might do with it really involve adding two numbers and just remembering the 0 to keep them apart. So we're really looking at pairs of real numbers. So this vector space behaves an awful lot like R2. So this subspace of R3 behaves a lot like R2. So if we have 1, 0, negative 3 plus 2, 0, 2 equals 3, 0, negative 1, that looks a lot like 1, negative 3 plus 2, 2 equals 3, negative 1. The only difference is we've got zeros in the middle here and we don't there. But all the calculations are exactly the same. That's what I mean. It behaves a lot like R2. It's pretty much doing calculations in R2. Alright, now let's look at another subspace of Rn. Let me erase this list up here so I have more space. Let's let A be a matrix with real entries. Let's say it's an m by n matrix with real entries. Let's let V be solutions of ax equals 0. So if a is m by n, then this is going to be vectors in Rn that satisfy that equation. So this is definitely going to be a subset of Rn. These are column vectors of n numbers. So the question is it a subspace? Well, let's check to see that it's closed under addition. So if we look at addition, and let's say we have ax equals 0 and ay equals 0. So these are two different solutions, x and y. So is x plus y going to be a solution also? We're wondering if we have one solution and another solution, is there some a solution? Is this subset closed under addition? Well, let's see what x plus y does. So ax plus y equals, since we can use the distributive rule, we've got ax plus ay. But if ax is 0 and ay is 0, this is 0 plus 0, so that equals 0. So yes, it is a solution. And so I guess it's closed under addition. Now let's look at scalar multiplication. So scalar multiplication, what happens if we multiply that by a number? Is it still going to be a solution? If we have ax equals 0, how about a times kx? All right, well, each equation ai1 x1 plus ai2 x2, etc. ai n xn equals 0. Now, x satisfies this, so each one of those equations is true. Becomes, when we multiply x by k, ai1k x1 plus ai2k x2, etc. aink xn. And then if everything here gets multiplied by k, I guess we can factor out the k. K ai1 x1 plus dot 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 ain xn. But this part is 0 because we took this from an equation that we knew was true. So this is k times 0 equals 0. So if every equation I works that way, then I guess k times x is a solution just like x is. So this set is closed under scalar multiplication and addition. So yes, it's a subspace. Now I picked ax equals 0, a right-hand side of 0, for a reason. Let's change this problem and look at solutions of ax equals b for some non-zero right-hand side. So is it a subspace? So let's look at addition. Is this closed under addition? If ax equals b and ay equals b, is x plus y a solution too? Well, ax plus ay equals ax plus ay by distributive law. And if ax is b and ay is b, then this is 2b. So I guess a times x plus y is not b, it's 2b. which is not the same as b unless b is a zero vector. So this is not going to be closed under addition if b is not the zero vector. So this is not a subspace of Rn. All right, now let's look at the functions and a subspace of functions. Let's let V be the solutions of y double prime plus a of x, y prime plus b of x equals 0. So a of x and b of x are functions. Sorry, I forgot the y. B of x times y equals 0. So what if we have two solutions to this equation? Two functions, y equals f of x and g of x. So we'll check addition, closure under addition. If y equals f of x and y equals g of x are solutions, then how about y equals f of x plus g of x? Well, we need its derivative and its second derivative to plug in here and see if we get a solution. So y prime equals f prime of x plus g prime of x, and y double prime equals f double prime of x plus g double prime of x. And if we plug these in for y double prime, and y, we've got f double prime plus g double prime plus a of x times f prime plus g prime plus b of x times f plus g. And what is that equal to? Well, if we separate out the f's and g's, we've got f double prime plus a of x f prime plus b of x f, and then g double prime plus a of x g prime plus b of x g. But if f of x, y equals f of x is a solution, that means that f double prime plus a of x f prime plus b of x f equals 0. So that means that this first part equals 0. And then if y equals g of x is a solution, that means that g double prime plus a of x g prime plus b of x g equals 0. So that means that, yes, y equals f of x plus g of x is also a solution. So we have closure under addition. Now let's check scalar multiplication. So if y equals f of x and k is a number, So if y equals f of x is a solution, and k of x is a number, then is y equals k f of x a solution? Well, the derivative is going to be k f prime, and the second derivative is going to be k f double prime. Because when we take a derivative of a constant times a function, it's just constant times a derivative. Then if we plug in that function and its derivatives into this equation, we get k f double prime plus a of x k f prime plus b of x ky equals, I guess we can factor out the k f double prime plus a of x f prime plus b of x f. But if y equals f of x is a solution, that means that f double prime plus a of x f prime plus b of x f equals 0. So that means that all of this is 0. So we've got k times 0, which is 0. So I guess k times f of x is a solution too. So that means that V is indeed a vector space. It's a subspace of the space of all functions. So it's a vector space. It's a subspace of the space of all functions. All right. Now once again, having this be a subspace depended on having equals 0 on the right-hand side. So let's change the problem and say this equals g of x and see what happens. So we'll check closure under addition. So if y equals f of x and y equals g of x are solutions, then how about y equals f of x plus g of x? So we've got f double prime of x plus g double prime of x as the derivative now, plus a of x f prime of x plus g prime of x plus b of x f of x plus g of x. And if we separate out the f's and g's, then we've got f double prime. I'm sorry, I didn't mean that to be g because, oh darn it. Let's make that right-hand side be h of x, because the g I'm using here has nothing to do with the right-hand side. It's just a solution. All right, so this is the, okay, this is what happens if we plug in the two solutions. And then if we separate the f's and g's, we've got f double prime plus a of x f prime plus b of x f plus g double prime plus a of x g prime plus b of x g. And if f of x is a solution, that means that f double prime plus a f prime plus b f equals h of x. So that part's h of x. And if y equals g is the solution, that means that g double prime plus a g prime plus b g is also h of x. But that's not the correct right-hand side. We were hoping that this sum, y equals f of x plus g of x, would be a solution to the equation. That means when we plug in all the derivatives, we should get h of x on the right-hand side, but we got 2h of x instead. That is not h of x. So that means that y equals f of x plus g of x is not a solution. So since we can't add solutions and get new solutions to this equation, I guess this space V is not a vector space. And that is because it is not closed under addition. The end.